Hi and hello everyone. What we have seen so far are Markovian queuing systems, but those systems can be modeled by a birth-death process, and hence we call that as birth-death queuing systems. In such systems, what was happening, that the arrivals occur singly, right, and the customers are also served one at a time. So, at any given point of time, there could be at most one event of either one arrival or one departure, right, nothing more than that. So, that makes us the state transitions to occur only to the nearest neighbors, and hence a birth-death process model which is a special case of a continuous time Markov chain was appropriate, and we could see that it can model quite a bit of a large number of systems which exhibit such a behavior, right. And the reason that why we looked at that as in a first place is that these are analytically very much tractable in a very easy way, and which makes our life easier, right, and from which we could get the insights about the systems very easily, and the methodologies can be put into operation in such simple models, which can then be easily extended to a more complex models, right, and that was the idea. And now what we are going to consider is still Markovian queuing systems only, but these are then modeled by a non-birth-death process, right. So, that is why we call this as general Markovian queuing systems. That does not mean that the previous ones were not, they were also Markovian queuing systems, right, but those were a specific class of Markovian queuing systems, which is what we have considered. But we will now consider models which can be considered or modeled by a general continuous time Markov chain. So, when we say Markovian queuing systems, we are looking for model which is Markovian model, but it is a continuous time Markov chain. So, it is still in continuous time, but in state space is discrete. That is the case that we have, but by a non-birth-death process. So, those models, now what they allow? They allow transitions beyond one step, right, with respect to the state, right. So, it could be still one step, but there will be some transitions which might go beyond. If it is restricted to only one step, then again you are going back to your birth-death queuing models, but here general one. So, they generally allow transitions apart from the one step, that nearest neighbor transitions, they do allow transitions beyond the nearest neighbor's case. Okay. So, those are the systems that, and corresponding models is what then we are going to look at it. Since this is still you are still remaining in the Markovian regime, you still have the Chapman-Kolmogorov equations holds good, backward and forward Kolmogorov equations are true, and the balance equations that we write for generally Markov chain, these are all still valid. So, what that makes? That makes the essence of the approach that we have adopted so far in handling a birth-death queuing model, that remains the same, and that is also applicable, and it also helps us to solve such non-birth-death Markovian models. What is that then the difference? The difference is the complexity might increase, as you might see, right. That is what is going to happen, and from here onwards, without any saying, we are not going to look at a queuing system and look at its transient analysis or time dependent behavior, where the initial state plays a role and you have a finite amount of time and in which you are looking at the behavior of the system. No, we are not going to look at that anymore, which we have seen already in the case of birth-death with simple models, and we saw the complexity, right. So, but for most of our analysis, the equilibrium analysis would suffice, we will assume, and we look at queuing systems that are only in equilibrium. Now, here onwards we are not going to look at, of course, certain models we can easily look at the transient behavior also in some way, but we will not do that. We will restrict ourselves to the equilibrium analysis. So, it goes without saying that from this point onwards in the remaining part of the course, we are going to look at queuing systems that are in equilibrium, right. That means we are going to do only the steady state analysis, okay, and we will not worry about the time dependent behavior, right. So, this is what we are going to do next, this general Markovian queuing systems, where the appropriate stochastic models that comes handy are a general continuous time Markov chain, which is a non-birth death type. The first one that we are looking at in such scenario is a simple generalization of what you would see to queues where the arrivals or service happen in one at a time. What we have now is what we call as bulk queues. What do they mean? That there are many systems in which the arrivals can occur and or services can be performed in groups, which we call in bulk or in batches, right. For example, when a bus or train arrives or leaves, people arrive or leave in groups, right. People may go to restaurant together and may be served in batches. Lift or elevators or boats handle passengers in batches, right. These type of systems were all what are known as in our language as bulk queues, right. Bailey 1954 introduced the concept of this bulk service in queues, and Gaver introduced the bulk arrival queues. The literature is now quite vast, and you can look at the literature for more. Again, we are seeing that it is a elementary introduction kind of thing only what we are going to see for these kind of models. So, but there are much more. If you want, you can look at the literature. Okay. Now, what we have bulk queues, right. We are not looking at any generalization of concept, we still want to be within that Poisson exponential or Markovian nature, right. So, but this can be modeled by a non-birth death, but still a Markov process, that is basically a CTMC. Okay. Specifically, we consider systems where either the arrivals are in batches or service is provided for batches of customers. These are the two types of bulk queues that we are going to look at it. Of which the first one that we consider is the bulk input or bulk arrival queues, which we denote it by this. Again, this may not be the common notation. Sometimes some books use the notation M in the superscript simply X without the square bracket, right. So, that will also be, that is why I said these are all may not be standard notations. So, we might have to be explicitly saying, but at least in our case, like we can be familiar that we will be using this kind of notation to denote the bulk arrival or bulk input queues. So, what is the description of the system? That so, this has all the underlying assumption that we had for an MM1 system, right. So, the arrivals happen, right, according to a Poisson process with rate lambda, service times are IID exponential with parameter mu, there is a single server, there is infinite capacity for queuing, first come first serve, and there is no dependency between arrival process and service process, and whatever the assumptions, these kind of assumptions that we have had for MM1, they are still hold true in this case. In addition, right, in addition we said that the arrival stream follows a Poisson process, but now the number of customers in any arriving module, like when we look at an arriving point, the time between two different modules or two different arrivals is still an exponential distribution with parameter lambda, but at each arrival instance the number of customers who arrive at that point of time is not just a single customer, but a batch. That batch size is what we call it by a random variable x, and that has probability mass function Cn, which means that with probability C1 the batch will be of size 1, with probability C2 the batch will be of size 2, and so on, right. This describes the corresponding probability mass function, and this is what is this x that is sitting on the head in a way in the superscript of this M. So, this system is what then we are describing by this, and whenever C1 which is equal to probability of x is equal to 1 is equal to 1, then this will give back, you give back the original MM1 system, right. And the total arrival process, now if you look at here, is a compound Poisson process, right, with x denoting batch size. You think of lambda n being the arrival rate of a Poisson process of batches of size n. Then this Cn, which is the probability of batch size, would be then lambda n by lambda, where lambda is the composite arrival rate of all batches, meaning that this is sum of all this lambda. So, this gives that proportion of arrivals with that particular rate. So, this is what then would be the probability mass function, where this lambda n is the arrival rate of batches of size n, which means suppose if you think that there is a first instant in which 2 customers came, then there is a second instant in which 3 customers came, then again there is another instant in which 1 customer came, then there is another instant in which there are 2 customers came. So, there is first instant and the fourth instance were 2. So, between these two, the time if you count, like that is what is exponential with this parameter lambda 2, right, like which each one you can differentiate, and each one of them is the arrival rate of the corresponding batch size arrivals. A batch of size 2 arrivals, if you think, then that will be distributed with exponentially with parameter this lambda, and for which the probability is this, right. So, this is basically lambda n by lambda. So, the total arrival process, if you look at it, right, if you are just counting the total number of customers that come during an interval, if you look at it, then that will follow, right. This is an overlap of all these Poisson processes, the superposition of all these Poisson processes, which will be a compound Poisson process. Now, you can go back and look at the generalizations that we described for a Poisson process, and at that point of time we mentioned that this compound Poisson process is what is going to be used in the case of bulk arrival situations, right. So, it is the total arrival process if I look at it. So, basically is a compound Poisson process, which means that in a bulk arrival queue, the arrival process, if you look at the total arrival process, that will be a compound Poisson process if you are looking at the number. So, as usual we are considering n, which is the number of customers in the system in the steady state, and the underlying process is still Markovian is what we are seeing, right. Now, this is a sample transition rate diagram, which is of course it is very difficult to depict completely everything, and it will become quite messy, but at least you will get an idea here. So, why do we call this sample? Because here this diagram gives the transition rate for the simple case of Mx Mq, where this x takes value either 1, 2, 3 with the corresponding rates lambda 1, lambda 2 and lambda 3. So, the sum of these is what is the overall arrival rate of that lambda, right. So, what is the transition that can happen? For example, when the state is in 0, right, only then arrival can make it to move to either state 1 or 2 or 3 with the rates lambda 1, lambda 2, lambda 3, meaning what? If a batch of size 1 arrives, for which the rate is lambda 1, it will move to state 1. If a batch of size 2 arrives, right, which can happen with probability C2. So, lambda times C2 is what is your lambda 2 is effectively, right. So, it can directly move to state 2. So, you see here from 0 it can move to state 2. So, it goes beyond nearest neighbors, whereas 0 to 1 is still nearest neighbor transition, but 0 to 2, and similarly if a batch of size 3 arrives, then it can move from 0 to 3. Since we assumed only these 3 batch sizes are possible, it cannot move from 0 to 4, right. So, the same thing can happen in state 1, 2 and so on. Say for example, if I look at in state say 2, right, what can happen? It can move to state 1 by service completion of a single customer. By the way, in this model you have to remember that the service does not happen for batch, right? Service is given by for one customer only at a time, right? So that is why with the rate mu, it moves from state 2 to state 1, or with the arrival of batch size 1 it can move to state 3, or with an arrival of batch size 2 which can move to state 4, or with an arrival of batch size 3 it can move to state 5 and so on, right. So this is a general which is 1, 2, 3 with batch sizes of this 3, and this is what would be the rate diagram. Now if you can imagine, suppose if you allow for all possible things, which means that what will happen, all sizes suppose if you allow, then 0 to 1, 0 to 2, 0 to 3, 0 to 4, 0 to 5, 0 to 6, everything, all arrows will be there. Now if you look at everywhere, somewhere here, like it will be quite messy, right. So you can see that, but that is the essence. So you need to catch the essence. Now once you catch the essence, generally in such Markovian models, general Markovian models, what is done is you look at a typical state and see the transitions into that particular state and out of that state, so that helps us to write down the general balance equations. Okay, that is what will be the general case. So now you look at here what happens here. So here we are looking at the state n, right. So we are looking at some generic state n, right. How the process can get into this state, general state n, right. One way is that you can get into this state n by a service completion, right. So that means n plus 1 it was, so one customer gets served and then the process moved to state n, and that is with rate mu, okay, that is one. The second, that is we are getting into the state, right. So this is the term that we write here, mu times p n plus 1 is what, that corresponding term, corresponding to the service completion of one customer. The other way how it can get into state n is from any of these states, right. Now suppose if it was in state n minus 1, okay, state n minus 1, and there was an arrival with batch size 1 for which the corresponding rate is lambda 1, and so with that rate lambda 1 it can come to state n, right. That is the first thing. Second thing is, suppose if it was in say n minus 2, right, if it was state in n minus 2 and a batch of size 2 arrives, then for which the corresponding rate is lambda 2. So with the rate lambda 2, this can move from n minus 2 to n with the corresponding rate lambda 2. So this red color thing, arrow that we have marked here is that generalization. So this lambda k, so the state was some n minus k, right, and with the rate lambda k from that particular state n minus k, this will come to state n, right. So the state, that is what you have here, right. So for example in 2, suppose if the state is in 2 with the rate lambda n minus 2, then it can come from state 2 to state n, right. Similarly if it is in 0, right, this can come to state n if it is possible that there is an arrival happens with rate lambda n, which means a batch size n, right, if it is what that is happening here, right. So in this particular case you can now see that what would be the state is n minus k, and with arrival of lambda k, then it can come to state n, right. That is precisely is what we are writing it here. State is, the current state is n minus k, and lambda k is given by lambda times ck, right. Remember ck is lambda n by lambda is what is Cn. So lambda times ck is effectively lambda k. So this is what is lambda k here. The current state is p of n minus k. With rate lambda k, this can move to state n. So this together on the right hand side will give you the rate of flow into state n, right. Now from here, from any of these state n plus 2 you cannot come to state n, and from 0 you can go up to n here, right. From 0, if with rate lambda n plus 1, if something arrival happens, means batch of size n plus 1, then from 0 it will go to n plus 1, not to n. Remember here in this diagram, only with respect to state n, the in and out arrows are marked. Does it mean that there is no mu here, there is no lambda 1 here? Please do not think, because that we have purposefully hidden, because just to depict the behavior with respect to the state n alone, right. This is what we have here, right, with respect to inflow into the state. Now what is the outflow? Outflow is as usual 1. Suppose when this is in n, when there is one service completion happens, that is with the rate mu, then it will move to state n minus 1. That is one possibility. The other possibility is arrival happens to when the system is in state n, or there are n customer in the system, and correspondingly it will move to some state. So what is that state? So with rate lambda 1, it will move to state n plus 1, and with rate lambda k, it will move to state n plus k, right. So this is sum of lambda 1. So that means that with rate lambda 2, it will move to n plus 2, with rate lambda 3, it will move to n plus 3, and so on. That corresponds to arrival of batches of appropriate sizes, right. So that is what will happen. So that is what this lambda case depicts. So the outflow is basically mu plus lambda 1 plus lambda 2 plus lambda 3 plus lambda so on. So all these lambdas, if you sum, what you would get is this lambda, right. What is this lambda? So this lambda here is sum of all lambda k's, where lambda k is from 1 to infinity, right. That is what you have here. So this is then the rate of flow out of state n, and this is the rate of flow into state n, and at equilibrium means these two flows should be at equilibrium, means that these two rates must be equal, and hence this equality here. So this is the generic equation, and at the boundary, meaning that what? Suppose if you push this n all the way up to 0, what would happen, right? So if I draw a line here, you would see that there is no left transition can happen, only the right transition will happen, and that is precisely the first equation, right. Mu p1, which is equal to lambda times p naught, with lambda is basically sum of lambda is, right. That is what you have it here. So that is the boundary state, that is for the state 0, this is what. So this together is what the balance equations, right. So writing down this generic balance equation is the most important step, for which you need to understand the system clearly, what is the transitions, how the transitions happen from one state to the other state, and what are the possibilities that you can think about it, right. So that is what will give you this equation. Now once you write down this equation, right, you see here the same essence what we did in the birth death q, in the same way only we are writing down this balance equation, but thing is that now things are a little bit complex. Apart from that, there is no other issue with respect to this here, right. So this is what is the balance equation. Now once you write this balance equation, right, then it is the question of now how you will solve. Okay. Again the methodologies, similar approaches can be adopted here there. Okay. So this is basically that these two lines describes the how the last equation comes up here into this. So to solve this equation, okay, we will use a generating function approach, but whenever this batch sizes are small, right, though theoretically here we set x is a random variable which has support as set of all positive integers, theoretically these are limited, and if the batch size is limited, suppose when a ferry comes, it cannot be that an infinite amount of passenger comes there. When a bus comes, right, it cannot be that an infinite amount of customer can arrive from the arrival of a bus, right. So that is all limited. So if the batch size is small, then the difference equation also can be used, but we will use here a generating function approach to solve this system of equations. Now for which we define two generating functions, C of z, which is generating function of the batch sizes, or the batch size generating function, and P of Z in our usual way. So, this is the generating function for the system size probabilities. So, these are the generating functions of the batch size probabilities, this is Cn, and the system size probabilities Pn. And if you look at here, since the batch size, this is an input to the system, right? You know what is the batch size, that is part of your model assumptions. So, this C of Z is known, and here this is an input. So, we need to find out from that what is P of Z and P of Z. From there, you extract to get the Pn's, and once you get Pn's, then you can do whatever the usual thing that you wanted to do with respect to the system state probabilities. Now, let us see how one can do. So, what you can do is that same trick here, that this is the system of equations. You multiply the first one by Z to the power 0 and the second one by Z to the power n, and sum over n from 0 to infinity, right. Then on the left side you will have this, right. The right side you will have this. So, what you are seeing here is this part, right. So, this part you look at it here, and this one you look at it here. So, this quantity, if you look at it, that is summation k is equal to 1 to n p n minus k c k, where p is a probability distribution, c is also a probability distribution, right, these probabilities, right. So, this is basically the convolution function of which gives you the sum of these two random variables, right. If you compute the sum of these two random variable, then that will have its distribution will have this as the form where that will be equal to, the sum will be equal to n, will have basically this form, right. So, this is the probability mass function of the sum of the steady state system size and batch sizes, and the PGF of the sum, because they being independent, the PGF, then only you will write it in this form, otherwise you will write it in the joint distribution form, right. So, the PGF of the sum then will be the product of the respective PGFs, right, which is basically what we are saying is this quantity, which is basically this quantity here, right, would be, you can write it in this form by taking the summation from k to 1 to n, you just interchange, okay, 1 to infinity and n from k to infinity is what you will get here. Now, this quantity is nothing but P of Z, this quantity is nothing but C of Z. So, that is what you will get. Anyway, you know this as a property, right. Sum of independent random variables, when you consider its Laplace transform or MGF or PGF will be given by the product of. So, that is what you have here. So, once you substitute all these things here, what you will get here is this quantity, right. What you will get here is this quantity, which is this. So, here mu is from n 1 to infinity, because in the first equation there is no mu term. So, that is what you will get here. So, that means this sum is nothing but P of Z minus P naught, lambda times P Z plus mu times this is mu by Z. Again here there is one term missing, so you will get this. So, this is exactly equal to lambda times C of Z, P of Z. Now, if you solve for P of Z, you will end up with this kind of expressions, which normally happens when you do this. Again here we have one quantity to be determined still, which is P naught, and as we have said earlier, this P naught will be then determined using this condition that is satisfied by this generating function, which is P of 1 equal to 1. Now, let us see how I can do this. Now, what you can do, this mu times 1 minus Z, you can divide by this. So, this becomes P naught by 1 minus this quantity, lambda by mu times Z, then C bar Z, something we are denoting it, where C bar Z is simply 1 minus C of Z by 1 minus Z, right. This is what you have. So, this is the form, we are writing it in this particular form. Now, you observe that this C bar Z is, what is this? This is 1 minus Cz by 1 minus Ez. So, which is nothing but this is the generating function of the complementary batch size probabilities, right. What is the complementary batch size probabilities? You take the cumulative distribution function and you take its complementary, which is what C bar n, which denotes now probability of x greater than n, which is nothing but 1 minus probability of x less than or equal to n. So, this C bar Z is basically the generating function corresponding to this C bar ends. So, the C bar of Z is C bar n multiplied by Z to the power n is the sum over n is what will give you this C bar of Z. So, you can simply work it out if you wanted to see this, otherwise it is not very difficult one. And the C bar is at the complementary batch size probability. The complementary CCDF itself plays a critical role in many different applications. Say for example, in reliability theory, where you look for survival of some instrument or machine or anything like beyond certain time point. So, you are looking at probability of x greater than n, or in actuaries for example, you look at the survival probabilities. That is why this is also called a survival function in those areas, right. So, this quantity is nothing but where C of Z is the probability generating function of the PMF of the batch size, right. Whereas, you take the CDF of that batch size and take its complement. For that function, if you find the generating function, that is what you will get as this C bar of Z, fine. Now, if you want, you can work it out, but anyway it's you can find it elsewhere in your text also, you will be finding it, fine. Now, you impose the condition 1 equal to P of 1, which will give you this quantity, right. Now, this is what you, because this is what your P of Z, so P of 1 is will give you this one, right. Now, but you still need to find C bar 1. So, now C bar 1 we have to find from this C bar Z, but then you have to apply L'Hopital's rule at least once to get to this. Now, once you get that, then what you will end up with this expression, which is nothing but expectation of x, that you can easily see. So, this is what then you will get as this C bar 1, which is the expectation of x is what then you will get as C bar 1. Now, once you substitute that, then you can get P naught equals 1 minus of lambda b mu times expectation of x, which is 1 minus rho, where rho is now the utilization factor of the traffic intensity of this particular model, because this lambda e expectation of x is what is the total arrival rate, right, and mu is the service rate, right. So, this is what then rho would be this utilization factor. So, 1 minus rho for any single server model in a typical way. So, that is what you get here. So, the rho is this quantity here. So, once you plug in that, then you know that P of Z is given by this expression. Now, if we are interested to find the explicitly the PNs, then we can find now from here where we have obtained expression C bar of Z is this. So, 1 minus C Z by 1 minus Z, you plug in here. So, what is the thing? It is everything expressed in terms of parameters, input parameters, right. If you know the form of C of Z, say for example, then you can immediately plug it and you can try to get it. So, which we can find if there is requirement and if it is possible and feasible to do that. Now, again you note here P naught equal to 1 minus rho. So, this will be strictly greater than 0 if rho is strictly less than 1. So, rho is less than 1 is the necessary and sufficient condition for the steady state to exist in the usual manner, like as usual you expect. So, this is what is the condition under which the steady state would exist in the even in the case of here in the MX M1 model, where my rho is now this, right, because this is the total arrival rate, lambda times expectation of x is the total arrival rate, that is what you will get here, right. So, this is once we have this, now if you want we can invert, and if it is possible, not just if you want, but it should be possible, and it is possible for many reasonable assumptions if you make with respect to batch size, then it is possible to invert it. Okay. Now, let us look at some of the performance measures. Of course, many things can be done, but of course, some of the performance measures is what then we will be seeing. It is the basic ones. Okay. What we have here is we want to find L from P of Z. As you know, L from this generating function is given by P dash 1. The first derivative of the generating function of the Pn's evaluated at value 1, which will give you this expression directly, and this now C bar of 1 we already know as from the previous one, it is expectation of x. So, at least you can substitute that, then you will get this expressions. Still we want C bar dash of 1, means the derivative of this C bar function evaluated at the point 1. So, which can be found again from the C bar Z, but now you have to apply L'Hopital's rule again. So, after finding this, you will see that you have to apply L'Hopital's rules twice to arrive at this expression. In a similar way, there also you would obtain here like C dash 1, but does not matter. So, here C double dash 1 by 2, but C dash x is basically the generating function of the batch size probabilities. So, this is nothing but the factorial moment, expectation of x into x minus 1 is what this C double dash 1, that is what we are writing it here. So, once we know this, now you plug it here, then you will get this expression which is equal to this expression which is equal to this expression, where my rho is lambda time expectation of x by mu, right. And here you will see in this form that rho by 1 minus rho is what normally you would find for the MM1Q, and this is multiplied by some such factor which is based upon the first two moments of the batch size probabilities. Similarly, like this is mean number in the system, say if you want to compute the variance in the system, you can then express, you will get an expression which we will not do here, but those of you who are interested, you might do if you want to know the variance of the system size, which will have a similar expression, but that will now involve the first three moments of the batch size probabilities, right. So, that is how one would get it, fine. Now, once we get this L, then by using Little's law and the box results that we have exhibited between W, WQ, L, LQ, right. So, we can employ Little's law to get the other quantities, but now you have to remember that the arrival rate of customers now it is simply lambda times expectation of x. So, the Little's law would then be L equals this arrival rate times W, where it is not just lambda, but lambda times expectation of x is actually now the total arrival rate. So, that we have to keep that in mind. Now, once we keep that, then my W is basically L over this arrival rate will give me my W, then WQ it is this W minus 1 by mu, because it is still single server and customers are served 1 by 1. So, W minus 1 by Q. Now, LQ, right, will be then the arrival rate times WQ, right. WQ is this. So, lambda expectation of x times W, which will give me L, and lambda expectation of x by mu, which will give me rho. So, L minus rho, right. Rho is, even in this case, the probability of finding a non-empty system, where but rho is basically this quantity, that is what you need to remember here. So, LLQ, WQ you can get here, right. But if you want waiting time distribution, but that is little bit complication, but then you have to look at now the two quantities. If we are looking at this is just a hint, okay, there is nothing that we are going to do with that, but I will just highlight the point when for some of you who might be interested to look further. Okay. The waiting time, total waiting time, suppose if you look at in the queue, this will be two components. One is the arrivals are happening in batches, right. So, his the number of customers who were arrived up to the previous batch, that will be one time, right. They have to be served all. Then within his batch, right, then how the his service time is going to come when, depending upon that there is another time. So, the sum of these two times will give you the total waiting time, and accordingly the analysis have to be carried out, okay, which even carried out even in the general service time distribution setup, people can look into that, okay. So, we will not worry about that, we are looking at the average performance measure with respect to these four. Now, with this in mind, like let us look at some of the simple examples, okay. As we said, the C1 equal to 1, meaning that there is only one batch of size 1 customer arrives, then all other CNs are 0, then you obtain from this result itself the corresponding results for MM1 model, which you can verify to confirm that this is actually the case here. On the other hand, there could be a constant batch size, which is so common, right, also. So, let us call this batch size to be some capital K, right. So, Ck, which is probability of x is equal to k, is 1, and all other CNs are 0. That is a scenario that you have here, right. Again this is a deterministic situation, but now batch size is not just 1, 2 or 3 and so forth, it is just a constant k. So, that at every arrival instant it is a constant batch that is coming, right. Possibly in many scenarios you can think. Okay. Now, this L, then if you use the formula there, like this is what you will arrive at, because this is what we have obtained this as L, right. So, or this any expression that you think, right, rho plus k rho, which you can write it in this form. So, this also we have written here, right. So, this is k plus 1 by 2. So, which is basically the MM1 mean system size, which is rho by 1 minus rho multiplied by this is what then you are going to get in this particular case L. Now, once you have this L, then LQ is L minus rho, and if you want W or WQ even in this particular case, you can obtain it using these expressions without, it goes without saying. Now, in this particular case, the inversion of P of Z to get the system size probabilities, they are also reasonably easy if the values that you assume for k is small enough. But if it is for large value, of course, then things will be difficult. But for small values, you can still do it. It's not going to be that much complex. Okay, that's what you might see. Another example could be a geometric batch size, really a random size that you have here. So, we have geometric alpha, which has this as the form of the PDF or the PMF here, sorry, it is a discrete. So, it is a PMF here. So, my rho is lambda time expectation of x. So, the expectation of x is 1 by 1 minus lambda in this particular case. So, that is what you will get here, and then the C of Z, which is basically this quantity, is essentially this is what is then input, right. That is what we said is an input to the model. Now, once I have this, now P of Z in the same expression, instead of this 1 minus C of Z. So, you substitute that here, right, you simplify and you make this is usual way, like you can write it in this form, right. You always try to write it in terms of this kind of quantities where because this is much easier, 1 by this quantity minus alpha Z by this quantity is what then you will be getting it here. Now, this is again a geometric series, this is again a geometric series, of course, multiplied by Z outside. So, but this quantity will give you a geometric series. Now, you pull out the terms corresponding to the Z to the power n, you will end up with this expression, which will give you this expression. So, in this case, the system size probabilities are also given by this expression, right. So, you can easily see that thing here. Okay. Now, let us take a typical example, which is exactly as presented in the textbook. Okay, so we are looking at a machine line production system, a process that produces an assembly in quantity, meaning that it is getting passed on to some other next work to be done on that. Okay, it passes through some number of stages. So, after the first stage, many items are found to have one or more defects, which must be repaired before they enter into the second stage, and this job of making adjustment to the defective items is done by currently a single worker, one worker. Okay. And the data suggests that the number of defects more than 2 is only a very small negligible amount. So, let us assume that the number of defects is either 1 or 2, which is what is happening in the most of the time. And the duration or the time between arrival of a single defective item and 2 defective items follows exponential with parameter lambda 1 and exponential with parameter lambda 2 respectively, where lambda 1 is 1 per hour, lambda 2 is 2 per hour is what is happening. And the service time, whether it is single defect or 2 defect, right, the service time repair each defect in this particular case, right, for the worker service time defect is basically 10 minutes is what it takes. Okay. Now, subsequently it was observed that the rate of defects have increased, and it was decided to put an additional worker who will then handle exclusively the 2 defect items while the original worker will handle exclusively the single defect item. The singlets and doublets is what then would happen in the scenario. Okay. Now, whether to add and if so when to add an additional worker will be based on a cost analysis, which would correspond to the average delay time of assemblies that are in for repair, and that is directly proportional to the number of in the system, means number which is waiting in the system for repairing. It is a repaired machines or failed machines, right, because the L is directly proportional to W. So, L is what then one can relate it in that manner. Okay. So, this is what is the setup. Hope that is clear. Now, with the original system where there is a single worker, there is either one defect or two defect with the corresponding probabilities, right, corresponding rates that would occur. We can analyze the model first. So, the total lambda is lambda 1 plus lambda 2, it is 3, mu is 6 because 10 minutes it takes, so it is 6. So, the C1, which is the probability of single defect is, so a batch of size single defect arrival is 1 by 3 and C2 is 2 by 3. So, the expectation of x, which means the average number of defects, is 5 by 3, right, and expectation of x squared is 3, which you can compute. So, rho would then be equal to 5 by 6 because it's lambda time expectation of x by mu, which is the utilization factor here, and L, which is this expression. Now, once you plug in the values, this will turn out to be say 7. Now, in this particular case, it is also nice and easier that you can in fact compute the system size probabilities, because the batch size are either 1 or 2 with the corresponding probability 1 by 3 and 2 by 3. So, it is 1 by 3 times Z plus 2 by 3 times Z squared is what is the generating function C of Z. Now, once you plug it that into that P of a Z, then you will get this expression. Now, there will be two roots for this. Now, you make the partial fraction expansion and make a series representation and extract the nth coefficient, you will arrive at this expression as the Pn's. So, this is what would be the Pn's, which means number in the system. One can obtain. Of course, we do not need at this point of time for our analysis as far as that what we are concerned now, but if required for such models, this can be obtained easily, right. Now, you can see for 3 and 4, then this thing will get a more number of roots, and then you have to find the roots of those or the zeros of that polynomial and so on, you have to find. That is what will be involved when you want to compute the system size probabilities. Now, for us this is what is happened. Now, let us do the cost analysis, for which we assume C1 is the cost per unit time per waiting repair, because the the way products are waiting for repair before they pushed into the second stage after the first stage, and the waiting cost, right, you associate with some C1, and C2 is the cost of the worker per unit of time, right. So, if you want to assign per unit time one worker, then what is the cost involved is what is C2. Okay. Now, in the original system, when there is only one worker, the system is really an MX M1 system with the assumption of only two possible batch sizes of either 1 or 2 with the corresponding probability C1 and C2. So, L you will compute it as expressed here using this expression, which will of course turn out to be 7, but that is the expression that you will use to get this L. Then the expected cost per unit of time of the single server system of operating this particular system is C1 times L, because L is the average number which is waiting in the queue in the system, and C1 is the corresponding cost plus one worker cost, which is C2. So, C1L plus C2 is the cost per unit time for this single server system, which is MX M1 system. Now, suppose if you are adding second worker. Now, what did we do? When the second worker is added, we decided that that new worker will handle exclusively that two defect items, while the original worker will handle the single unit items, single defect items, right. So, when the second worker is added, remember that additional C2 cost, we are assuming that both the workers have the same cost C1 and C2. If that is the case different, then of course you have to change it that one. Okay. So, but now we now have two queues. The single defect items, if I look at it, right, it is a simply M1 queue which is handled by one server, because the original worker handles this, he handles only single defect items which arrives at the rate lambda 1. So, this MM1 with arrival rate lambda 1, service rate mu and single server, for which my L1 is this particular expression. Simple. Now, the doublet line is basically this model, but now with a fixed size 2, because it is exclusively 2 defect items is what is being handled by the new worker, right. So, this is basically batch size is 2 is what that you have. So, the correspondingly this process, right, you adopt the constant batch size model to arrive at this L2, which is what arrive at this L2. So, the average number of units in the system, right, is basically then L, which is the sum of these two quantity. This is the new L with the addition with the second worker added, L1 plus L2, which is equal to this. Now, if I look at the corresponding cost here, right, the cost will be the new cost, if I call it as some C star, which is C1 times L, right, and now 2 workers are there. So, it is 2 times C2, right. So, this is the new cost. So, this is the new cost and this is the old cost where this L is as given for this MX system here. Now, what will be our decision criteria? Any decision then to add or when to add or to add this second worker would be based upon the comparative magnitude of this C star, C and C star, the comparison. So, an additional worker will be added provided this C star is turning out to be smaller than C, right. So, now what is C star is this expression, C already you have an expression. So, that means that you want this to happen. Now, L if I substitute for this 1 C2 you can get rid of. So, you will get this expression, okay, and where C1L is L is this is what is the expression which is equal to this expression. So, basically C1 times this plus C2 should be less than C1 times this, right. Now, you have lambda 1, lambda 2, mu, everything you have all these expressions. So, that is again you can simplify it in this form. Now, if you plug in all these values, so you will arrive at that value to be 19 by 5. So, using the parameter values, then we can obtain the decision criteria to be this, right. Now, an additional worker is involved or is added provided the C1 C2 satisfies this relationship, otherwise it might be good idea from the cost perspective to continue with the single worker, right. If the cost of the worker is less than roughly 19 by 5 times, it is not roughly, it is less than this times the cost per unit of weighting that you are associating. So, depending upon these two costs, then the decision can be taken whether to add second worker or not. Now, the same can be reversed, similar analysis can be reversed if you are given C1, C2, suppose if you want to determine the rate at which the service need to be expanded or anything that you want to decide with respect to that, one can also do a similar analysis along these lines. So, this is one simple example of how one can use these kind of models applicable for any model that you have done so far, right. So, when you are basically comparing these kind of things that you have it here. Okay. So, this is about the bulk arrival models that we have seen today, right. So, this is what we are going to. So, for more of course, you can look at literature, but we are not going to deal anything beyond at this level for the bulk arrival models here. Okay. So, we will see in the next lecture. Thank you. Bye.